Another oxidation we can talk about is oxidative cleavage. So that's where we can take a double bond and actually snip it in half, making one alkene into two molecules that have carbonyls. So carbonyl has C double bond O in it. What we'll end up doing is taking where there was a CC double bond, and it'll have a CO double bond there in each of the two sides that were clipped. So ozonolysis is one way we can do that. Ozone, which is O3, is produced by just sending oxygen gas through a little chamber with a spark and some sort of electric discharge. So there are machines that can produce a constant supply of ozone with a spark inside of it. So what happens, ozone adds to the double bond, so we got 3 oxygens going across that double bond. It then does a strange rearrangement where the CC bond is broken and one of the oxygens is placed in between the 2 carbons. So don't worry about the mechanism for that. It's all kinds of arrows going all over the place. It's not important right now. This ozonide has the CC bond broken with 2 oxygens across in one direction and 1 oxygen across in the other direction. But that doesn't even stick around for long, because that can even be explosive if it's isolated, especially because it has that OO bond, which we learned was so unstable. What you can do is use a reducing agent like zinc in order to break the CO single bonds, right, and replace them with double bonds. So it's an overall reduction, because not only are we breaking 2 CO single bonds, we're also breaking an OO single bond as well. So the overall net effect of this, I'm not so concerned that you know too much about these intermediates here. What I am concerned with is that you know that ozonolysis occurs by taking an alkene and splitting it right down the middle and capping it off with CO double bonds, where there once was a single CC double bond. So that's all there is to ozonolysis. It's, again, 2 steps. Step 1, O3. Step 2, ZN. Okay? So you need each of those steps in sequence. If you want to use a single arrow, put 1 O3 above it and then 2 ZN below it. You have to show that it's 2 steps, just like a lot of these. But really very simple product, right? You cleave the double bond, you form a C double bond O in its place. The substitution of the double bond determines whether a ketone or an aldehyde will form. Ketone has 2 R groups attached to the CO double bond. An aldehyde has just 1 R group and an H. So if there was an H on one side of the double bond, if you do ozonolysis, you'll make an aldehyde. So let's do ozonolysis of this one here. This is a tetra-substituted double bond, so it has 4 R groups coming out of it. So because of that, I'm going to make 2 ketones. All right? So break straight down the middle of the double bond, draw everything up to the double bond, except instead of connecting the double bond to the rest of the molecule, just make C double bond O. Same thing with the other part. O, then double bond C, and then in this case 2 CH3s. So in the other case here, let's break the double bond right down the middle. This is a di-substituted double bond, so each side of it has 1 H. So that means we're going to make 2 aldehydes, where we made ketones above. So CH3, CH2, 7, CH, and now C double bond O instead of the double bond to the rest of the molecule. So same thing, O double bond C, still that same H attached. CH2, 7, C double bond O, OCH3. Notice C double bond O is not affected. Just like how catalytic hydrogenation only reacted with the CC double bonds, the ozonolysis will only break CC double bonds. CO not affected, CN double bonds not affected. Right? A similar sort of process is oxidative cleavage using potassium permanganate. So KMnO4, that'll also cleave an alkene, but the difference is that instead of just leaving it as it is, if there were any number of hydrogens on that carbon, those hydrogens will be replaced with CO bonds. So it will be oxidized further because potassium permanganate is a strong oxidizer. There we go. So we will have no aldehydes. Aldehydes, if we form them as an intermediate, will continue to be oxidized to carboxylic acids further. So let's just summarize here. There's a large molecule. Let's just make this whole thing over here R, so I don't have to draw that out. So R, CH, C double bond, CH2. Okay. So R, CH double bond, CH2. Potassium permanganate will break the double bond. So as an intermediate, I'll have R, CH, C double bond O, then plus O, C double bond, CH2. This was a terminal alkene, so there were two hydrogens on the end of that double bond there. So as a first step, we just cleave it, much like ozonolysis would. Okay. In fact, I'm going to call those ozonolysis. I'll say like ozonolysis products. But potassium permanganate continues to oxidize. Right? So you don't need to draw all these arrows if you don't want to, but where there was an H attached in this aldehyde, we'll now have R, C double bond O, OH. Okay, we'll have a carboxylic acid. In the other product, which was formaldehyde, O double bond CH2. That will be oxidized all the way. So what's as oxidized as I can make one carbon? Well, C double bond O, another double bond O. Okay, so if we have one H on that side of the double bond, we'll end up with a carboxylic acid. If we have two H's, we'll end up with CO2. It's important to note, though, that if I just have a regular tetrasubstituted alkene, I could use either. Right? If I used KMnO4, I would do oxidative cleavage and get two molecules, in this case of acetone, so two ketones. Ketones, since they have no H's along those C's there, they cannot be oxidized. Ketones cannot be oxidized. So it stops there. Turns out we would get the same products if I did ozonolysis. So tetrasubstituted double bonds, it doesn't matter if we use permanganate or if we use ozonolysis. Right? So same products. So that hopefully shouldn't be too difficult. Just practice cleaving a double bond, right? Snip it right in half, like with the scissors or something. Replace it with O's that cap off what once was the double bonds, so do C double bond O's. If we use ozonolysis, that's it. If we use potassium permanganate, any H's on the same carbon as that C double bond O will be oxidized further. So carboxylic acid or to CO2.